So good morning, everybody. Today, I'm going to talk about the control of Dextran and Fructose in Louisiana Sugarcane Factories with Commercial Biocides. And I'll be doing this with Stephania Imbachi-Ordonez, who you heard yesterday. So why did we do this study? Well, for the last couple of years, I've been informing everyone we have new information that we have high and consistent amounts of fructan polysaccharide in Louisiana cane products right across the factory. And we know a major source of the fructan is from microbial degradation. But what we didn't know is if any of the current commercial biocides used in the factories right now control fructan. So that was the major aim of this study. And also because Louisiana factory staff kept asking us if all the current commercial biocides used in the factories control Dextran, we added Dextran to the study. Okay, so basically there are three major types of biocides currently being used in Louisiana factories: bleach, which is sodium hypochlorite, sodium permanganate, and that's a more recent addition, and sodium carbamate, which tends to be a mixture of two carbamate solutions. So to do our study in controlling Dextran and Fructose, we took a two-pronged approach. And in this case, it was important because the laboratory results helped us underpin the factory results. It's not always easy with the changing cane quality and juice quality all the time to do the factory study. So in this case, the laboratory study underpinned the factory study. So we did juice deterioration studies, and we did factory biofilm formation, which Stephania will talk to you about. Now, the juice deterioration, we've done it on fresh juice from factories and frozen juices. But today I'm just focusing on the pre-frozen juice and the biofilm, but we do have more results. So if we look at these commercial biocides, we looked in the literature and all the reports. So there are, like everything, advantages and disadvantages. So bleach is an oxidizing biocide. Compared to chlorine, it's medium oxidizing efficiency. Advantage are obviously readily available, and compared to the other biocides, it's inexpensive. But it's known to irritate the skin. It certainly can corrode surface materials in the factory, low penetration power, environmental concerns, and it doesn't work in alkaline pHs, but actually that's not a huge problem in our sugarcane factories because where we add biocides, it's an acidic pH. Sodium carbonates are non-oxidizing. So the advantages: non-corrosive, high penetration power. They're actually more persistent than oxidizing biocides. FDA approved, and compared to sodium permanganate, it's relatively inexpensive, but it is more expensive than the bleach. The disadvantages with non-oxidizing biocides is you usually have to shock feed them. That means rather than dripping like 5 ppm all the time into your juice, it's better to shock feed at higher concentrations. And finally, sodium permanganate, that's an oxidizing biocide. We had a hard time finding its oxidizing efficiency to chlorine. We think it's medium. Some of the advantages is it has been reported to improve juice clarification and evaporator scale buildup. Now, disadvantages, the literature shows excess can cause corrosion, particularly iron corrosion. And there have obviously been limited studies on its use as a biocide or sanitizing agent in the sugar industry. And as I stated earlier, compared to the other biocides, it's relatively expensive. So I'm going to discuss the biocide laboratory experiments that we did at Audubon. So we took a grass reduce, stored it at -80, but when we came to do the experiments, we coarsely filtered it. We just wanted to take out those large bacillo and gas particles. We conducted all the juice deterioration experiments at 25 degrees C, which is room temp. We just left them, and we looked at 4 different concentrations of biocide, 5, 15, 30, and 45 ppm. And we allowed the experiments to run from 0 to 36 hours. Everything was done in duplicate, and we ran them in a random order for statistical analysis, and there was always a control of water. So once they're deteriorated and we've taken the aliquot samples, we measured the pH and the optical density, and the rest was frozen until we could analyze them. And we analyzed dextran, mannitol, fructan, and sucrose. So here are the pH results. So if you look here at the top here, this is a typical juice deterioration curve. At the beginning, because it was frozen, we killed a lot of the microbes in the juice. So it was obviously being recontaminated with microbes in the air or whatever. So this is just a lag phase, which just means the microbes are growing slowly. But the fact that the pH goes down here is because you had considerable microbiological growth. Juice is full of nutrients, so microbes are gonna grow, and then it tapers off, and that's because metabolites formed on deterioration actually build up and knock out the microbes. So this is a typical curve. Now at 5 ppm, basically with an experimental error, we're not seeing much difference with any of the biocides. There may have been a little with the bleach. At 15 ppm, you're definitely seeing carbamate and bleach starting to delay microbial growth. Gets even better at 30, and it's exceptional at 45 ppm, and the bleach was slightly better than the carbamate. But the permanganate always followed the control, water. We looked at optical density because some microbiologists, they use this as a measurement of microbial growth. So typically, as the microbes are growing, you would find an increase in the optical density. But when we looked at these coarsely filtered pressure juices, basically, we were not finding any real difference. It was not giving us any information about microbial growth, so we stopped using that. Okay, mannitol is a very sensitive indicator of leuconostoc deterioration, which is also the major, but not the sole, microbe forming the dextran. And mannitol tends to form earlier than high molecular weight dextran. So at 5 ppm, you can see that obviously mannitol is forming on degradation. It may be bleach is slightly slowing it down. By 15 ppm, bleach and carbamate are definitely slowing it down, and so on to 45 ppm. Again, the permanganate followed the control. Antibody dextran, this is high molecular weight dextran that we measured. So this is the dextran that causes problems in your factory. Increases viscosity, elongates the crystal. And you can see again at 5 ppm, not a great difference between the biocides, but by 15 ppm, carbamate is doing a particularly good job, and the bleach. And the same again to 30 and 45 ppm. Again, the permanganate followed the control. And then fructan. So the first thing you can see here is that fructan, once again, we're confirming that a major source of fructan is juice deterioration. So at 5 ppm, you may have a little bit, bleach is helping a little bit, but we actually found carbamate doing a good job at 15 ppm, but bleach and carbamate was certainly helping control fructan. There may be differences here between the biocides, bleach and carbamate, because different microorganisms are forming the fructan. And Dr. Giovanna Aita at Audubon is actually doing a study right now, and she's already identified a few microorganisms that are forming the fructan. And then sucrose. Obviously, this is one of the huge problems with microbial deterioration in factories. We're losing a lot of expensive sucrose. So all the sucrose results kind of backed up what we've been seeing with the microbial deterioration markers. So again, at 5 ppm, not much differences with the different biocides, but by 15 ppm, carbamate's certainly improving sucrose losses. We have to repeat the bleach on this one. By 30 ppm, carbamate and bleach are doing a good job, and 45. So these biocides not only are controlling the microbial deterioration, but they can also control expensive sucrose losses. So now I want to pass the chair over to Stephania.
Good morning. I'm going to present the factory biofilm experiments. So in the early and middle parts of the 2020 grinding season, excess biofilm or slime formation occur on the rotatory vacuum filters in factory A. Okay. Although we know that biocides is not normally applied in the vacuum filters, we took this opportunity to study the efficiency of the biocides in controlling biofilm formation. And we were able to develop this kind of experiments at scale, at factory scale. So here you can see some pictures of the biofilm that we found in the rotatory vacuum filters. Here you can see a lot of slime. Here, all this is a slime that we found in this particular factory. So what is biofilm or slime? Biofilm form when microbes adhere to surfaces in most environments by excreting a slimy glue-like substance. So the bacteria here adhere to this surface and they start producing different components, like in sugar factories, they can produce dextran, they can produce fructan, protein, and all these biofilm can trap mud particles or juice particles. Here in this picture, you can see the biofilm that we found. And in the factory, we see that the biofilm is dark because it could trap these mud particles. So what we did, so we used raw iron coupons like the coupon that you are seeing here, and we installed those coupons in one rotatory vacuum filter in the factory A. So this is a scheme of the rotatory vacuum filter in the front, and this is the back of the rotatory vacuum filter. And we installed the coupons on this wall, in the inside of this wall, and we installed 10 coupons. 5 coupons on this size were used for the treatment, and on the other side we installed another 5 coupons for the control without any treatment. And we spray biocide on this side of the wall with the coupons. So we spray biocide every 2 days for a week, and this is like the schedule that we use. The first day we install the coupons. We clean the filter before before installing the coupons with hot water and steam to be sure that we remove all the biofilm from the filter. Then we install the coupons. We spray the coupons with the biocide. In this case, we use bleach, And 2 days later, we spray again and so on. At the end of this week, we remove the coupons, we weigh the coupons, and we clean the filter again, install the coupons again for the next treatment. And this is the schedule that we use. We spray 1 gallon of each biocide in the coupons. This is around 125,000 ppm, and it was a shot treatment. These doses that we use is not a doses that we are recommended. It's just a doses that we choose to test in this experiment. So before each treatment, we weigh the coupons, we clean it with ethanol, and then we install the coupons. And at the end of each treatment, we remove the coupons, we weigh it again, and we put it in water and keep it on ice and transport them to Audubon to final analysis. So those are pictures of one of the experiments. In this side, you can see the control. This is the wall where we install the coupons on the other side. And you can see biofilm formation here. But with bleach, you can see that in this area, the production of biofilm is lower than with the control. And this is one of the coupons. So you can see a lot of slime here, but after the bleach treatment, you can see an important reduction of the biofilm formation. Those are the results. So in contrast to the control, bleach significantly decreased the biofilm formation in the coupons. You can see here differences between the control and the bleach, around 54% of reduction in the biofilm formation. Carbamate and permanganate also reduce biofilm formation. You can see that here, around 24% with carbamate and 15% with permanganate, but without any statistical difference. And water, in this case, almost followed the control. And the addition of water increased 8.6% the biofilm formation. So it was evident that the biofilm trapped more mud particles, so we measured conductivity ash to prove this. Bleach and carbamate behave similarly, so they trap less mud. And permanganate followed the same behavior as the control water. So with the use of permanganate or with water, the mud particles in the biofilm increase. The protein content is a major component of biofilm. So protein decrease with all the biocides and generally follow the same trend as the laboratory deterioration experiments that Dr. Gillian just showed. And you can see here that bleach reduce the production of protein with significantly the different statistical difference. And with fructan, we can see that the highest reduction of dextran was obtained with bleach, around 13%, but without any significant difference. With fructan, we know that it's also a major component of biofilm. Permanganate, in this case, was the only one that significantly reduced the fructan production. But we are concerned about the analysis with dextran and fructan because we can have some interferences in this methodology because we have a lot of mud particles in the biofilm. So we are going to do more studies to be sure that those results about dextran and fructan are good results. So as conclusions for both experiments, from the laboratory experiments, we can say that with factory crusher juices, optical density was not a good measure of microbial growth. Bleach and carbamate control mannitol, high molecular weight dextran and fructan at doses higher than 5 ppm. Generally, permanganate followed the control with water, and the overall efficiency of the biocides is this here. So bleach was the best one. In some cases, the results of bleach were similar to the results with carbamate. Both biocides were better than permanganate, which was similar to the control. In the case of factory biofilm experiments, we know that fructan was a major component of biofilm at the factory. Bleach significantly decreased the biofilm formation, the protein production in the coupons. Carbamate also reduced the biofilm, protein, and dextran production, but without any significant difference. And there were not as strong differences among all the biocides in controlling dextran and fructan because, as I said before, we have some interferences with the methodologies. And with those results, we can say that permanganate significantly reduced fructan. So the overall efficiency of the biocides is that bleach in this case was the best one. The next one was carbamate. Both of them were better than permanganate, which was a little better than the control. So the biofilm experiments was not as conclusive as just deterioration experiments. Those more studies must be done. Then I want to acknowledge to the American Sugarcane League for partial funding. I want to thanks to factory staff for all their help. And I also want to thanks to Saint for his technical assistance. Thank you so much.